So here's our basic UART test program. It's just a very short looping program, and I've added a 10 millisecond delay so it makes it a little bit easier to trigger on the oscilloscope. So the first thing I want you to notice is that we have a variable called switch count that I'm using just to hold some data, in this case the number 25. And on line 7, we're going to be configuring serial port 2, which is on the transmit data pin 2 or TX2, which is connected to pin 16 on the Arduino. And in the looping part of my program, all I'm doing is printing out the letters MH, and there's an ASCII code for those letters. And then after that, I'm printing out the value of switch count, which in this case should be 25. And then I want to look at that on the PicoScope. The first thing I'm doing here with this PicoScope is I've set up the trigger to none. And that's very good when you just want to confirm that you actually have a signal on the data line. And in this case, I do see something happening, so that's a good sign. And if I want to stop it, I can just click up here. One of the things I can do very quickly is I'm transmitting at 9600 bits per second. 1 over 9600 is equal to 104 microseconds per bit. So what I want to look for is that if I look at one of these bits, and notice I'm at 200 microseconds per bit, and this looks like a bit that's probably about 104 microseconds wide. So it tells me I probably got some good information. The next thing I want to do is set up the trigger. And if I change the time per division, I'm just going to make it 1 millisecond, run it again. And notice that I have a long pulse. If I stop it here, there's a long pulse that's high, and I'm going to use that to help trigger my signal. So I'm going to go to a trigger mode called auto, and then I'm going to change the type to pulse width. Make sure this is equal to pulse width. The source is channel A. The threshold, you want to be some value between 0 and about 5 volts. So I'm going to use 2 volts. And a threshold level of about 3%. And that's going to be fine. There's not going to be any noise in that area. But we do want to set the pulse direction to positive, greater than a certain value. And since our delay here, if you look at the time, that's 1 millisecond. There's 1, 2, maybe we'll set this to 2. So what we're looking for is a gap here where it's greater than 2 milliseconds. So now that I've done that, I'm going to run it again. And that's great. It looks like it's triggered now. I'm seeing all my characters, but that's not serial decoding. So to serial decode, I have to come over here and click serial decoding. And this is the UART. So I'm looking for RS-232 UART, and we have that now. So one of the things I want to make sure is that my data is on channel A, which it is, the blue channel for me. Threshold can be anywhere from about 2 to 3. So let's just make it 3, and this a half a volt. The other thing that's important is make sure that you have the correct bit per second or baud rate and the number of data bits. It's parity is equal to none, stop bit 1, and least significant bit first. Once you've done that, select next. And here, a good choice is to display ASCII on the graph, and maybe hexadecimal in the table, because there's a graph and a table. Okay, and now you can actually adjust this. Make sure that your reference for this channel is at 0 volts. It's on a 0 volt line, and let's get it running. Okay, so if you recall, my program is outputting my initials, MH, a space, and that's actually a 20, and then the value 25. This represents a carriage return and a line feed, which just means the data is being printed to a new line. Now down at the bottom here, I can bring this up, and then we can look at the data in hexadecimal. So an M is 4D, H is 48, a space is 20, and then 32, that's the number 2, 5, and then this is the carriage return and the line feed. So everything is working as expected. Okay, so this is my trigger. Notice that I have it set to 1 millisecond per division. Let's just check that UART setting. Make sure all your settings are like this. And the other thing you might want to do is set up a measurement for time. Okay, I'm going to get this out of the way because I don't really care about that. But the time ones you drag from the left-hand side. So I want to start at the beginning of the start bit, which is right here. Okay, you got to make sure it's just before that 0. And the end of this, it's going to be just after the stop bit. So the start is the 0, the stop is the 1, and these are the 8 bits of data. So in total, you have 10 bits. So make sure that when you do your calculations, it's going to be the number of characters, so 1, 2, 3, 4, 5, 6, 7, times 10 bits for each character. So that's 70 bits, and we're operating at 9,600 bits per second. So you could actually take the 70 and divide it by 9,600, and that will give you your time. So I've put cursors between these 2 points, and up here it tells me the time between those cursors. So I think that's everything for this serial I/O. My next program is the I2C basic test program. So it looks like this. The important thing here is to include this library called wire.h. This is required whenever you want to work with I2C devices. And then you start off by saying wire begin. And this is setting the clock frequency for the I2C bus. And we're using a standard speed of 100,000 bits per second, which is 10 microseconds per bit. And so the next thing I want to do is to make sure that I'm transmitting to the correct device. And we're using the MCP 4725 DAC. It's a 12-bit DAC. And the address for it is 60 hex. That's the UART address. Then this next command is there to make sure that the next few bits of information that we send are going to be used to update the DAC. Okay. If we were using switch count, this is the place we'd want to send the data. But I'm going to start by changing this to FF because I want to get the maximum voltage that I want to measure. And then since this device only has 12 bits of information, it requires 3 hex digits. FFF. And if you recall, this last 4 bits is disregarded because we only need to send 12 bits of information. And at the bottom, we have this delay. This is going to make it a little bit easier to trigger the PicoScope. Okay, so that's it for the program part. All right, the first thing that I did up here was to make sure that the trigger was set to none. I'm using I2C. And I've set my scope trigger or scope time base to 1 millisecond. So all I'm looking for here is that I do seem to have data on the 2 channels. This tells me that the program is running correctly. So I do have these 2 channels. So the next thing to do is to set up the trigger. So I'm going to go to trigger and I'm going to set it to auto. I do want to use pulse width. And since the signal here, most of the time it's high, I want to have a positive pulse. I'm going to set it to greater than 2 milliseconds. That's what I added some time in the software to help with this. Threshold, somewhere's in the middle. And the hysteresis, if there were noise here, it would help to reduce the triggering. So 3%, 5%, I think all of those are going to be okay. All right. So now that I've done that, I want to use a more appropriate time base so that I can actually see the data. And that might be a little too wide and this might be a little bit too low, but I think this one will work out. So it's triggering on that edge. So that's all okay. So the next thing I want to do is to go to, I'm going to delete this one. Okay, that was for the UART, and I'm going to add serial decoding. And this time it's for I2C. So I'm just going to select this one. And the clock signal, you can tell here that the clock signal is the top one. So my data is on B, my clock is on A. And for the threshold, anywhere between 2 and 3 is okay. And 4 or 500 millivolts is okay. You can see I'm using a standard bus speed of 100 kilobits per second. And that's what I had configured in the program. And that would give me about 10 microseconds per bit. Once I've done that, just move ahead. You can use hex and decimal. Use one for the chart and one for the waveform, and then everything else is defaulted. Okay, so get the program running again. Make sure you click this running button. Make sure as well that channel B has a 0 ground reference, channel A, and you can move these obviously up and down here, and you can move this up and down. Make sure it locks in at 0 volts. And you can actually move this a little bit out of the way if you want. And then the other thing I might want to do is move everything up so I can see the numbers down here. Okay. So the next thing I want to look at is that everything seems to make sense. Well, the first thing is that you'll see there are 4 groups of clock pulses. This is for the first byte, second, third, fourth, right here. The address we specified was 60, and these are hexadecimal values. And then update the DAC was 40, and we're sending out FFF. Remember that last 0 is disregarded. Now that we have that information, everything seems to be okay. The next thing I've done is to bring up the Elvis meter, NI ELVISmx meter. I've set it to the 20 volt range. And the reason why that's important is I want to get that extra 1 digit of precision, which I do have here. And the first thing that I'm doing is setting it to measure the supply voltage. And mine's kind of low coming from the USB port of my computer, but it's still okay. And I'm getting about 4.5 volts. Okay, so I'm measuring that, and that's when I'm outputting the maximum value of FFF. Okay, 4.5 volts at 3F. So what I'm going to do next is adjust my program slightly so that I'm outputting 7FF, which should be half. And I can see that my data now is 7FF, which should be about halfway. The previous number was about 4.57. This is 2.26. So that's about halfway. So looking at the waveform, besides the address, you'll see these little green symbols here. That is actually the that we're writing to the device. So it's address, we're writing, we're getting an acknowledgement, which goes low, acknowledgement after this data. And you can actually see there's a little menu that comes up giving you all of the information. Acknowledge, acknowledge. And I've put cursors between the start and the end of the data so you have some idea how long that message was. And you can see the bits of information. And if you were to measure the time, they're operating at 100 kilohertz, which is 10 microseconds. Okay. If we go to the I2C decoding, you can see again that the clock signal is on channel A, it's the clock. B is the data, and these are the threshold levels. Okay, and standard mode of 100 kilobits per second. And then on the screen we have hex. We could change it to decimal, but let's just try that. So now this is going to be decimal, but it's less useful for us because these numbers make a little bit less sense. So we want to see these in hexadecimal. So you can go back up to here and go to the second screen. Probably hex is the best format. Sometimes you might want to see it in binary, which we can do in the table, but now it's in hexadecimal over here. All right, that's it for this presentation. Now we're going to be working with the SPI program, and you'll notice that we're using pin 4. That's going to be the chip select, which is on pin 1 of the rheostat. Then we have SPI begin, and this is where we're telling it to operate at a megabit per second, most significant byte first, and SPI mode 0, which causes it to idle low. And then we're going to make chip select go low. At the end, we're going to make it go back high, and we're sending out 2 bytes of information. One that says select the first rheostat or channel 0, that's the 00. And then we're going to output a value which is at the maximum of FF. Okay, so that's all that we're basically doing in the software. All right, I'm starting off with trigger set to none. Very useful in just verifying that you actually do see something. So right now I have one channel connected to the clock, that's channel A, and the other one connected to the data. But I'm going to do one more thing. I'm going to change the clock to the chip select. And I just want to make sure that I get something there. So this is with it connected to +5 to ground. This is a great way to test that everything is working. This is the chip select right here. And then this is the clock signal. So I seem to have some meaningful information. Then I'm going to go to, one more thing to notice is that most of the time, the pulsing signal is a logic low. So we want to have a negative pulse. We're going to be measuring pulse width. My source is going to be the clock on channel A. So now I'm going to go to auto mode. And that seems to freeze things in a place we'd like it to be. Now I'm going to zoom in a little bit by changing this to a lower value. And now it seems to be a little bit more meaningful information. I have two sets of clocks, so number of bits here and a number of bits here. For my data, which I know is 0, 0, 0, and FF. So I like my setup for my trigger. So auto, source A, 2-volt threshold, that's this point right here. A little bit of hysteresis, and that's 5% of the overall range. We have a negative pulse on the clock signal, so it's mostly low. And when it's greater than 2 seconds, after that, we want to trigger. And that's why we're getting a trigger edge right here. Once we have all that set up, then we go to our serial decoding. And this is the serial decoding for the SPI. You want to select this one, SPI serial data IO. So I'm turning that on. My clock signal is on channel B. My data is on channel A. As I said, this can be 2 to 3 volts, 4 to 500 millivolts. So I'm just going to make this a standard value. Don't worry about any of this. We want our clock to be triggered on a rising edge, that first rising edge. Chip select doesn't get used here. The most significant bit is first. The length of the information is 8 bits. So once we've done that, move on. We'll select our graph to show us hex and maybe the table to show us decimal. And then click finish. Okay, and then we want to get this running. I'd stopped the recording momentarily because I noticed it wasn't triggering. And then I went back to look at my decoder and I'd put the data on A. But the A is actually going to be the clock and B is going to be the data. And then I'm going to select next and finish. And now I have something meaningful. Before I wasn't getting any information. So this is serially decoding the SPI data, telling me that the first byte is 00, the second byte is FF, and that was matching up with my program. So let's just review that. So I had to make sure that the data was on B and the clock was on A. For me, the blue channel is the clock. So everything works out correctly. And what I'm going to do next is just pause this. Now I've brought up my Elvis meter so that I can measure the resistance, and I'm measuring the resistance between pins 5 and 6. That's the rheostat. Make sure that you select the 20 kilo ohm range. That will give you the best resolution. So I have 9.80 kilo ohms. And that's when I'm sending out the value FF. So I'm going to make a modification to my program. So I think I'll bring up my program, and we're working with the SPI, which is the rheostat. So here's my program, and I'm going to change it to the halfway point, which is 7F. Okay, download that or upload that program. Okay, and once we've done that, we're going to go back to the measurements and notice what happened to the resistance. It's about half of what we had before, and the data is now reading 00 for the first rheostat and then 7F. Okay, so again, let's just look at let's just delete this decoding. Okay, and we'll add it again. So you go to serial decoding, and we want to use this one here, SPI SDIO. And the mistake I made before was selecting the wrong channel. So my data is on B, my clock is on A, everything else is as expected. And then we're properly serial decoding, and then I can bring up my meter. And this is where I can actually change the value. Let's get it running again. The meter up here, I can change it to whatever value and then monitor what's happening on the meter. Now, since the maximum was about 10 kiloohms, 10 kiloohms divided by the 256 gives me, I think it's about 3.9 ohms per bit. So have a look at the trigger, the voltages that we used here, the time that I have this set up, and also if you wanted to look at the serial decoder, you have that information here. So I hope all this helps when you're doing the lab. All right, this is just a little bit of a review of the connection to the two different devices that we're using. So the MCP4725 is a DAC, and we're actually going to be measuring the voltage from ground, which is on this pin, to the V out, which is on this pin over here. Notice here there's no wires connected in here, but you do need to connect those wires. These need to be connected to the serial clock and the serial data line on the Arduino. Okay, and so that's the DAC. Coming over here to the right, this is the SPI connections. We have the serial data in. That's going to be connected to master out, slave in. This is the serial clock. That'll be the serial clock on the Arduino. And this is going to be pin 4 on the Arduino that selects that particular chip. To measure the resistance of the rheostat, that'll be done with the Elvis meter between pin 6 and pin number 5. So this is a diagram of how you'll be connecting the hardware. So this is for the I2C 12-bit DAC, which is going to have a range of 0 to 4095, and in hex that's 0 to FFF. So it's 12 bits or 4 or 3 hex digits. Remember, in the software, the least significant hex digit of the second byte, we don't use it. Okay, so it has 2 bytes, a low and a high. You're going to be connecting your PicoScope to these 2 signals, channel A to the clock and channel B of the PicoScope to the serial data so that you can monitor what's happening. So that's the hardware. And then the pin that you're going to connect the Elvis meter to is the V out pin with respect to ground. For the rheostat, it's the 8-pin chip that we're going to be working with, and the rheostat is actually connected between pin 6 and 5, so that's where you're going to add your Elvis ohmmeter. And it's a device that has a range of 0 to 10K, but be aware that it's plus or minus 20%. So one of the first things that we do is to actually measure the maximum resistance by setting this register to FF. And we're going to be connecting our oscilloscope to 2 pins. So the channel A is going to be connected to the serial clock, and channel B is going to be connected to master out, slave in, which connects to the serial data. And then we're measuring the resistance up here.